Okay. So not lecture 10 maybe, but. All right. Yeah, so you'll also have to forgive me. I started to make excuses, but I wasn't supposed to give this lecture either. The last time I looked at these slides was 1 year ago, and there's some jokes in here which I don't remember the punchlines to. So you're going to have to help me out. Okay, so every time I click, it'll be like a little surprise to me too. Okay, so we're going to talk about probability, which is one of my favorite topics, actually, and it's very relevant for computer science because it's such a great tool to use in analysis and design of algorithms. I know you've seen it before, probably, but we're going to do it all again just to make sure we're on the same page. And hopefully, there'll be at least a little bit that's new to you here. Okay, I'll skip this slide. This is going to be like a fun game, but we only have so much time, and I don't have the little interactive thing. But does anybody know what's happening in this slide? Has anybody seen this like kind of puzzle or trick before? Okay, so these are all like dice with just like non-standard numbers on the sides, and there's 4 of them. This one has like 4 copies of 7 and 2 copies of 1. This one has like 3 copies of 8 and 3 copies of 2. And like you can play the following game. I would do it, but anyway. You go to your friend and you say, you choose whichever die you want, and then I'll choose a die, and then we'll both roll our dice, and whoever gets the higher number wins. And so it seems like you're being nice to your friend by letting them choose first. They'll choose like the better die, right? But actually, these dice have the amazing property that like if you let your friend choose first, then you can always choose a die that's like better than them. So like if your friend is like, oh, I'll choose this like 7, 7, 7, 1, 1 die, then which one should you choose? D. Yeah, D does seem to look like it sort of dominates A. Like you'll win with a higher probability with D than with A. But it's like cyclic. Like A, D is better than A, and C is better than D, and B is better than C, and A is better than B. So it's like. Thank you. Thank you. I don't know if you can see that. It says, to Luis von Ahn. He wasn't even supposed to lecture today. Like, he definitely will not be here today. I'll be sure to give it to him. Man, this class is just filled with surprises, isn't it? Well, now let's talk about probability. That's enjoyable. Okay. Let's see. So, now I remember the point of this anecdote. So, let's cast our minds back to France in 1654, which is when probability as a mathematical discipline began. And there's some dude called Chevalier de Marais, and I tried to find a picture of him, but I couldn't, so this is just some dude. And I guess like he was like a high society dude, and he would go around to like his high society of friends and let's play a betting game with them. And he said, I'll roll a die 4 times, and I'll win if I get a 1. And I guess he, thought this was a good trick because, maybe your naive conception is that like, oh, there's a 1 in 6 chance of getting a 1. So if he only rolls 4 times, then, it's a losing bet for him. But of course, he'd play this bet with people and like make money. And we'll see why shortly. So I don't know what I was going to say here. But, as we'll see shortly, I mean, this is like a winning gamble for him. And so after a while, people stopped making bets with him. Actually, can somebody... Never mind, I'll come back to it later. So then he's like, oh, I need to invent a new scam. So he invented a new scam, which is like, I will roll 2 dice 24 times. And, he says, I'll win if I get double ones. And his conception was, since like, trying to get 1 1 with 4 rolls was good, you add 1 more die, that's like times 6. So he's like, I'm going to try and get 2 1s with 24 rolls. And that should make me money too. So he played it for a while, and then he started to be losing money. This bothered him, and he's like, I need to understand what's going on here. I thought I had a great scam. So he had some other scam going, and it was basically this situation. He was, I guess, really into gambling. And he said, imagine Alice and Bob are flipping a coin. It's like the simplest betting game of all. Alice gets a point for heads, Bob gets one for tails, and it's like a race to 4. And whoever wins gets 100 francs. And he said, suppose like Alice is up 3-2, and then like the game gets broken up. Like, how should they divide the money? Because they shouldn't just split it evenly, because sort of Alice was winning, but like, how much was she winning by? Like, how much money should she get? So this was a question that actually bothered him, and he thought about it, and he actually wrote letters to like the most famous mathematicians in France at the time, these people, Fermat and Pascal, and asked them to help him out. And they corresponded about this problem, and it was no joke. It was like literally this correspondence between Fermat and Pascal, which like started probability theory as an area of mathematics. So the moral of this story is actually, you may think it backwards, like, probability is a great field of mathematics, and you can also use it to help you out in understanding gambling. But it's actually backwards. Like, probability was literally invented to help people analyze gambling. So it's a very practical subject matter. Okay, so we're going to talk about computer science in particular, not just probability or gambling. So when I read textbooks on probability, I don't like them very much. I think they explain things in a bad way, so I will explain them to you in my way. And I really genuinely think, even if I weren't teaching a computer science course, I would still want to say that probability theory, you should think about it as analyzing code, like computer science code, that has random number generator calls in it. Okay? That's really the best way to think about probability, even if you're not a computer scientist. Okay, so what do I mean by that? How do you think about classic probability scenarios as code? Well, if somebody in your textbook says, Mary throws a 4 6-sided dice, you should just immediately in your head translate this into like this line of pseudocode. Okay? So I'm going to use this pseudocode function called randint to mean like give me a random number between 1 and the parameter. 1, 2, 3, 4, 5, 6. Okay, so you should just immediately go from here to this in your head. Okay? So this will be like a good way to formalize what it means to have like a random experiment or whatever, and it'll be better for mathematical analysis. Okay, so if instead Mary threw one 8-sided die and one 3-sided die, which these actually exist, especially in probability land, you always talk about n-sided dice for n not equal to 6. That's the 8 one. That's a 3-sided die. 2-sided die is just a coin. So you would just translate it to this. Okay? So what we're going to define an experiment, a probabilistic experiment, to just mean a block of code that includes some calls to a random number generator. Okay, so even if you see something like this, you immediately translate it into this. Okay, so you understand, like if somebody has 10% chance, you pick a random number between 1 and 10. If it's 1, they have the disease. If 0, they don't. Now, actually, this is a little bit like too much effort. Like if you want to generate 11%, you're like, oh, now what do I do? Okay, so so far I've given you access to one random number generator, randint, which gives you a number between 1 and 10. I'm going to give you access, or we're going to allow analysis of one more random number generator called Bernoulli. Okay, and so this is like a weird name, but it dates back to these French people that started the topic. Bernoulli is a random number generator that takes a real number p between 0 and 1, and it returns 1 with probability p and 0 with probability 1 minus p. Okay? So like if you plug in 0.1, it gives you 1 with probability 10%. Any questions? Okay, so let's see. Yeah, so if I say somebody flips 2 coins, that's like a 50-50 draw of 0 or 1. You can convert these to heads or tails if you want, but usually we'll just stick to 0s and 1s. So this would be 2 coin flips, Bernoulli half. So you don't have to do this if you don't want to, but you can if you want to. Okay, so just to recap, these are the 2 random number generators which we will allow when we're doing analysis of randomized codes, randint given m, it returns a number between 1 and m with probability 1 over m each, and this one returns 1 or 0 with probability p and 1 minus p. Now, actually, if you're used to some programming languages, it will seem as though I've omitted one that you're used to. But this one was not allowed for us. So you might want this one, uniform, that gives you a random real number between 0 and 1. Okay, that's the one you commonly see. But we will definitely not allow this ever in this class, because analyzing code that has this, kind of random number generator in it is much harder. Because there are like infinitely many outcomes, even more than infinitely many somehow. Okay, but you can still do most of what you would ever want to do with these two things. Okay, so now we understand, like if you have let's say a textbook probability problem that's described in English language, the first thing you do is model it with some code. And now it's good because you have like a non-ambiguous math problem. And now we can talk about how to analyze the properties of randomized code. So here's like a random problem. Mary flips a fair coin. If it's heads, she rolls a 3-sided die. If it's tails, she rolls a 4-sided die. Okay, so what is the code for this? First we do a flip. And we'll just call 1 heads and 0 tails. And then we either do randint 3 or randint 4. Okay, is that clear? Okay, so this is going to be our method for analyzing this situation, something called probability trees. So I will do this by an example. So here's our code that we're going to analyze. And the way it works is you go through the lines of the code one by one, and you make a tree, and there's like a branching in the tree every time there's a call to a random number generator. Okay, so the first line of the code calls Bernoulli a half. That's 1 or 0 with probability a half. And you put a branch for the two outcomes, which I guess here I labeled by heads and tails, but I'm identifying that with 1 and 0. Okay, and then you follow the code more along each, to sort of continue with each branch. So here you see if the flip came up heads, then the next call to a generator is a call to randint 3. So we write that here. And it has 3 outcomes, 1, 2, or 3. So you put a branch for each. And if it did come up tails, then you call this randint 4, and you put a branch 1, 2, 3, 4 for each of the outcomes here. Okay. And then now you've covered all the lines of code. And now you label the leaves with what are called the outcomes. Okay, and the outcomes just means like the list of all returns from the random number generators along that path. So this is the outcome, heads then 1, heads then 2, heads then 3, etc. Okay, that was not a definition. It was like a definition by example, kind of. But it's a good time to pause for a question. Okay. Okay, so now the last thing you would do if you're drawing this tree is for each of the outcomes, you write the probability of that outcome. And you get that by like multiplying the sort of associated probabilities along the path. So like, what's the probability of this outcome? Heads 1. Can somebody shout it out? Yeah, 1/6, because this had probability a half, and then this had probability a third, so you multiply them and get 1/6. Okay, and this guy is also 1/6, and this is 1/6. And what's the probability of tails 1? 1/8, yeah, because it's half times a quarter. Okay, good. And you may notice that, as you might expect, these numbers all add up to 1. Like, that accounts for all possible probability of outcomes. Okay, so here are some definitions. And an outcome is just a leaf in the tree, okay? So it's like return values for like all the calls to generator in one like execution. And the sample space is the set of all outcomes. Okay, so in this thing there were 7 different outcomes. And each outcome has a non-negative probability associated with it, and all the outcomes probabilities will sum up to 1. You can, I think, easily convince yourself of that by induction, I suppose. Okay. So far we just sort of set up the problem. So now, like, you might get a question about the scenario, such as, what is the probability that the die roll is 3 or higher? Okay, these are all sort of trivial questions, but I want to make sure we're on the same page. Okay, so this thing is what's called an event. Okay, and an event is just a subset of outcomes. It's a collection of outcomes, not all of them necessarily, but some of them. So in our case, it corresponds to 3 outcomes: heads 3, tails 3, and tails 4. All the outcomes where the die was at least 3. Okay, so it's a set of outcomes, and we define the probability of an event, S, to just be the sum of the probabilities of the outcomes. Okay, so here in the picture, S is all the outcomes where the die was at least 3. So it's this outcome, and this outcome. And the probability would be whatever 1/6 plus 1/8 plus 1/8 is, which is 5/12. Okay, I want to make a word about notation here. So actually, we have a slight overload of notation because we'll sometimes write, this is probability of an outcome, where S is like, a probability of an event, where an event is a set of outcomes. So we write that as probability of S. But we'll also occasionally write just probability of the outcome itself. So that's a little operator or notation overload. Okay, questions about these definitions? Okay, so let's look at problem, I think. So let's go back to this problem where Alice and Bob are just like flipping coins. First one to get 4 of the one they want wins, and Alice is leading 3-2, and then the game is broken up. So this is what Fermat and Pascal thought, which is a reasonable thing to think. It seems fair that the amount of money you should allocate to Alice is, the total pot, 100 francs, times the probability that Alice would win if they had kept playing. Okay, that's not like a mathematical statement, but they're just like, okay, it seems like that's a fair thing to do, so the next task, therefore, would be to compute the probability of this event, the probability that Alice would win. Okay, so let's do that as like one more illustration of how to solve a simple probability problem. So imagine the scenario where Alice is leading in this game 3-2. And the next thing that happens is they flip a coin, which in our terminology is like doing Bernoulli 1/2. And it can be either heads or tails. And in this case, Alice, who's going for heads, wins. So like the experiment is over. And otherwise, it's tails, and now the score is 3-3. So they flip a coin one more time, and there's heads and tails. Here Alice wins, here Bob wins. Okay, so that's the whole experiment. And so we label the leaves by the outcomes. So this is the outcome heads, this is the outcome tails heads, and this is the outcome tails tails. There's 3 outcomes in this experiment. And then we write down their probabilities. So what's the probability of this outcome? Half, yeah. And then this one is a quarter and a quarter, right? So this one's a quarter because it's half times a half. And then you usually circle, let's say, the event that you care about. So the event that we care about is Alice wins, which is this outcome or this outcome. So we circle it and like add up the probabilities. Oops. And we get that the probability that Alice wins is 3/4. Okay, so I think this is stuff that you've kind of done before, but I like to present it in this way, with randomized code and with trees. Okay, so I think this lecture has like a lot of definitions and stuff, so hopefully we'll get through it without getting too tired. Okay, so let me tell you some basic facts about events and probabilities. So remember, if you have an event A, which is a set of outcomes, then its probability is defined to be the sum of the probabilities of the outcomes. So if A is a subset of B, then of course probability of A is at most the probability of B. And the probability of not A, or like the outcome A not happening, the complement is 1 minus the probability of A, because the probabilities all add up to 1. And here's like one more important rule, which should remind you a little bit of inclusion-exclusion. The probability of A or B happening, this is the event of A or B, is probability of A plus the probability of B minus the probability that both events happen. And this is a very common fallacy, but I know you would not make this mistake to think that the probability of A or B is the sum of the probabilities. But I want to warn you against that. Actually, one thing that is true, of course, is that the probability of A or B is always at most the probability of A plus the probability of B, because the true probability is this, and we're just getting rid of a subtracted term. And this looks like the most trivial fact in the world. It's called union bound sometimes, but amazingly, this is one of the most powerful facts in probability out there, even though it looks so trivial. I once heard a famous professor of complexity theory, not here, say that this is the greatest fact he knew in all of his research, which I thought was taking it a little too far. But it is a useful fact. Okay. So let's talk about his original gambling games, and we'll, I guess, compute their probabilities. So in his original gambling game, you roll a die 4 times, and he wins if he gets at least 1-1. So here, it's a little annoying to draw a whole tree because, well, how many outcomes are there here? Yeah, 6 to the 4, right? Because he does 4 times something with outcome 6. So let's schematically draw it in our heads. And an outcome here is a path of length 4 down this tree. So we might label it by something like a 4, 6, 1, 2. That's he rolled 4, then 6, then 1, then 2. And all of these outcomes have the same probability, which is 1 over 6 to the 4. Okay, so let W be the event that Murray wins. So that's all the outcomes where there's at least 1, 1. Okay. Let's see what the next click of the slide says. So if we want to compute that, it's a little tricky. You could do it, but it's a counting problem, basically. You need to count how many sequences of numbers between 1 and 6 of length 4 there are that don't include any 1s, which is a little bit of a pain. And it's easier to compute the probability of the complement, the number of outcomes where Murray doesn't roll any 1s. So can somebody tell me how many such outcomes there are? Yeah?
1 minus 5, 6 to the 4th power.
Well, you gave me the whole solution. I just asked how many outcomes are there where Murray doesn't win. But I think it was right. Yeah? Yeah, 5 to the 4, just because each digit can be either 2, 3, 4, 5, or 6, and there's 4 digits. Okay, so the probability of the complement event is 5 to the 4 over 6 to the 4. So the probability that he wins is 1 minus this, which if you put it into a calculator is 52%. So this is why he was making money off this gamble. It's slightly better than 50% odds for him to win. Okay, so then he moved on to this next gamble, right, where he rolls 24 times and he's trying to get double 1s. Does anybody know what double 1s is called in gambling? Yeah, you guys are hardcore gamblers. I guess so. It looks like a number of, I guess it's also an animal term. Okay, so how are we going to compute the probability that Murray wins in this game? Oh, I guess I was supposed to ask you, but I'll just tell you. Okay, so I mean, each time he rolls, there's a 1 in 36 chance that he gets double 1s, and so there's a 35 and 36 chance that he doesn't get double 1s, and the probability that all 24 of his rolls fail to be double 1s is 35 over 36 to the 24. So the probability he wins is 1 minus that, which turns out to be 49%. So this is why he was losing. Any questions about this? Okay. So moving right along, in some sense we've talked about all the basic definitions and rules of probability. So you can set up any probability experiment you want and try to reason about the probability of anything you want. But now we're going to start talking about additional concepts. And one of them is conditioning. And conditioning basically means revising probabilities based on some partial information that you have. And you might say, what does partial information mean? It sounds like a flaky term. It just means an event. Okay, so conditioning on the event A is sort of like assuming or promising that event A actually occurs. So I'll give some example that I think that will help us out. So let's go back to this original experiment where you flip a coin and then either roll a 3-sided die or a 4-sided die. And we looked at this event S, the event that the roll is 3 or higher. And now we're going to intuitively talk about what does it mean to condition on S. So it's like you do the experiment. Let's say your friend does the experiment and then tells you, hey, event S happened. Doesn't tell you how it happened, but your friend just tells you event S did happen. And now you have differing opinions about the probability of each of the outcomes. For example, suppose your friend tells you, yep, I did the experiment and S happened. What do you now feel about the probability of the outcome heads 1? Yeah, 0, right? It evidently did not happen because the die was at least 3. Here's some notation we use for this. This bar means conditioned on. Okay, so this is the probability of the outcome H1 conditioned on the event S. And we agree that it should be 0. So I'm going to, again, by illustration, give you the definition. Okay, so in our revised world, this event has conditional probability 0. This event also has conditional probability 0. Okay, so now it gets trickier. Let's talk about this event, the event of heads, 3. What do you feel? It's up to you. What do you feel is the conditional probability of the outcome heads 3, given that you know that S occurred? I heard 1/3. You said 1/3. Why do you feel that? That's true. Still, do you feel it's equally likely that it would have been any of these 3 possibilities? Does somebody else have a different opinion in the back? Yeah, you say 1/6 over 5/12. Why? Yeah, kind of. So there's 2 competing ideas. The one that we go with in the definition is this one, 1/6 over 5/12. And the idea behind this, I'm trying to think of a good way to explain it. Imagine like your friend did this experiment like 1,000,000 times. Okay, then you would kind of feel that like 1/6 of the time it would have been this, 1/6 of the time it would have been this, 1/6 of the time it's this, 1/8 of the time it would be this. And so, if your friend now tells you, oh, it's the event S happened, it was one of these 5 over 12 times 1,000,000 outcomes where it was this, and of those outcomes, 1/6 of them were heads 3. So that's why we would feel that the conditional probability of this outcome is 1/6 over 5/12. So that's 2/5. So let's finish it off. This one is 0. This one is 0. And now the conditional probability of tails 3, given this event, will be 1/8 over the sum, 5/12. That's 3/10. And this one will be also 3/10. So this is 3/10, this is 3/10, this is 4/10. So yeah, it's a bit funny. Can somebody say like an intuitive explanation maybe why, once your friend tells you they got at least 3, it's like a little bit more likely that they got it via heads 3 than the other 2 possibilities? Yeah?
When you look at it, like it's a 1/6 overall, and the other 2 1/8 overall. So, like their relative probability is the same.
Yeah. Yeah, actually, I don't know if I have like a great answer to this question, but anyway, this is the case. Okay. So I guess we're going to do another example here. Let A be the events that tails was flipped. So let's circle that. Okay, I know what I want to say here. So once we condition on the event S, it's like we have new probabilities for all the outcomes. But they still are like normal probabilities in the sense that like they add up to 1. So it's like kind of a new probability law or distribution. And you can ask about the probability of events conditioned on some other event. So this probability is just the sum of the conditional probabilities of the outcomes in A. So that would be those 2. So it would be 3/10, 3/10, which is 3/5. So this is like saying if your friend promised you, did the experiment and promised you that the roll was at least 3, the chance that their coin flip was tails is 3/5. That seems natural, I guess, that is bigger than a half because there's more ways to get bigger than 3 on a tails roll than on a heads roll. Okay, so that was an example illustration. Here we'll give you a formal definition. Okay, so let's say you have an experiment, which is like a block of randomized code, and you have some event A, any event A, that you're going to condition on. And it should be a non-zero probability event if you're a super math nerd, to be careful. Then we just define the conditional probability of an outcome L to be 0 if L is not in the event A. And otherwise, it's the original probability divided by the probability of the event. Does that definition make sense? Somewhat? Okay, and so therefore the probability of, now you can define probability of events, like of an event B, that would be the sum over all outcomes L and B of the probability of that outcome conditioned on A. And now some of these terms are 0. The ones that are not in A are 0. So we can just do the sum only over the the outcomes that are in both B and A. So here I'm summing over outcomes in B and A of this thing, probability of L over probability of A. And now here the denominator is the same everywhere, and in the numerator we're summing all the outcome probabilities that are in B and A. So this is like a formula that you can remember if you want. The probability of B conditioned on A is like the probability of B and A over the probability of A. Okay. I'm going to give you one more formula here, I guess, called chain rule. So if you just invert this, if you multiply both sides of this formula by probability of A, you get this formula. Probability of A and B equals probability of A times probability of B given A. And I kind of usually remember this formula with a little sentence in my head, like, what's the probability that A happens and B happens? I say to myself, well, first A has to happen. The probability of that is probability of A. And then conditioned on A happening, B also has to happen. So that's where you get this term probability of B conditioned on A. Okay, here's the sentence I just told you. Okay, so you may expect or even already know this rule that if you want to know about the probability of the AND of 3 events, the probability of A and B and C all happening is the probability that A happens times the probability that B happens given that A happens. Given that and conditioned on are synonyms, by the way. And then now it's times the probability that C happens given that A and B both happened. Okay, so this is a formula. I mean, you can't prove it by just telling that little story I said, but you can prove it easily by going back to the definitions and doing a little arithmetic. Okay, and it extends to any number of events like this. Okay, so I guess I won't prove it because it's a little bit boring, but maybe in a recitation or something. Okay. Any questions? So I'm going to do a little problem now that involves conditioning. So let's say you have 3 bags, and you know that one of them contains 2 silver coins, one of them contains 2 gold coins, and one contains 1 silver and 1 gold. Have you seen this problem before? All right. So I'll just go quickly, and you'll get the answers. Okay, so you pick a bag at random, and then you pick a coin at random, and it's gold. What is the probability that the other coin in the bag that you picked is gold? If you've seen it before, you just shout out the answer. Okay, evidently it's 2/3, which, if you're let's say you haven't seen this problem before, like me, then, you're like, oh, I picked a gold coin, so it's, one of these 2 bags, and I don't obviously have any additional information. So, I kind of know it's down to one of these 2 bags, so it's sort of 50-50 whether the other coin is gold or silver. That sounds like a nice story, but if you actually, carefully translate it into, code and draw the trees and compute the probabilities, you'll just see that it's wrong. And somehow the fact that you chose a gold coin makes you sort of more likely to be in this bag. So here's how you would solve it formally. Let G1 be the event that the first chosen coin is gold, and G2 the event that the second chosen coin is gold. Imagine you subsequently choose the second coin in the bag. So you're asking, we're trying to find probability of G2 given G1. So probability of G1 is, what is the probability of G1? So who said a half? Robert? Yeah, why? Yeah, basically, yeah. I mean, the coin you choose is going to be one of these 6 sort of uniformly at random, and there's 3 gold coins. And what's the probability of G1 and G2? So in words, G1 and G2 is the event that both the coins are gold. Yes? 1/3. Why? Yeah, the only way this is going to happen is if your initial bag is like the middle one. So that's a 1/3 chance. And so by the formula, this probability is 2/3, as you all predicted. So well done. Pat yourselves on the back. Oh, I wonder how many more slides there are. OK. So I come to another important formula. And as I said, sorry, there's a lot of formulas and stuff. This one is sometimes called law of total probability. And it's really like the workhorse formula, like the way by which you typically actually calculate stuff when you have a probability problem. It looks a little bit long. But again, I kind of remember it with a sentence. Suppose you're trying to compute the probability of some event B. And somehow you feel that event A is relevant. Then you can compute the probability of B sort of based on knowledge of how A and B interact via this formula. And I'll read the sentence. I would say to myself, what's the probability of the event B? Well, perhaps event A happens. That's this probability. In which case, the probability of B is probability of B conditioned on A. Or perhaps A doesn't happen. That's this probability. In which case, we're looking at the probability of B given that A does not happen. That's the sentence I just said. Now again, yeah, OK, here's the proof. So this sentence is a good reminder. It's not a proof, but the proof would look like this. Let's look at this term here. Probability of A times probability of B given A. Well, we know by an earlier formula that's the probability of B and A. And similarly, this is the probability of B and complement of A, or not A. Now, this left-hand side is the sum of all the outcome probabilities for outcomes in B. And every outcome in B is in exactly one of B and A, or B and not A. Okay, so it's like you've partitioned B into the outcomes that are in A and the ones that are not in A. So the right-hand side and the left-hand side are counting up the same sum. In pictures, if you have sometimes you might draw a sample space like this. Remember, sample space is the set of all outcomes. So it's a set, and you might just draw it as a blob where the dots are the outcomes. So if A is some event, that means all the outcomes that are in A. And then A complement, or not A, is all the outcomes which are not in A. B is some other set. This is B and A. This is B and not A. OK, and so the probability of B is the sum of the probabilities of all the outcomes here. And so we're just breaking it up as the ones in here plus the ones in here. OK, again, there's a more general version of this, which allows me to introduce a definition. So let's say that events A1 through AN are a partition of the sample space. And that's like a set theoretic term. A partition means like a bunch of subsets that such that they exactly cover the space. So every outcome is in exactly one of the sets. And for any event B, we have this formula, which is like a generalization of the previous formula. In the case, the previous formula is like the case where A1 is some A and A2 is the complement of A. And A and its complement always form a partition. So here's the formula here. The probability that B occurs is sort of like either A1, A2, or A3, or up to AN must occur. And then you take the probability of that AI occurring and the probability of B given that AI. Okay. Any question about this? I won't do the proof is the same as basically this one. It's just this in this picture, instead of breaking up all the outcomes into 2 pieces, it'll be into n pieces. Okay, so here's a nice example problem. Again, maybe you've seen something like this before. Suppose I roll 101 like normal dice, 6-sided dice. What's the probability that their sum is divisible by 6? Well, now we're going to start to solve problems. If you were like a naive person, you would start to draw the probability tree, but it would have 6 to the power of 101 leaves in it, so you would never finish. So we have to be a bit smarter about what we're going to do. And the trick in this problem, this is a problem with a trick. This trick is to condition on the sum of the first 100 dice. Okay, if you haven't seen this before, you might not think of this trick, but I'm telling you the trick. Okay, so let's consider the outcomes of the first 100 dice. They're going to sum up to some number k. Okay? And for each possible number k they might sum up to, I'll define an event, a sub k. So what possible values could k take? Yeah, between 100 and 600. Okay, so we have 501 different events that we just defined. It's a very productive sentence. And I claim that these partition the sample space. And that's just because every outcome is in, has one sum, so it's in exactly one of these events, a sub k. Okay, now this is the event that we care about, b, the event that the sum of all 101 are divisible by 6. And we're going to try to figure it out using the law of total probability based on this partition, a100 through a600. And here's the main claim in yellow, that once we agree on this claim, we'll basically be done. I claim that for every value of k, 100 all the way up to 600, the probability of b, that the final sum is divisible by 6, given a sub k, is exactly 1/6, independent of k. And what's the reason? Well, let's say you conditioned on, the first 100 summing up to some number k. Like your friend flipped those or rolled those first 100 dice and told you, hey, they added up to k. Well, then you know that the final sum, after you roll one more die, is going to either be k plus 1, k plus 2, or up to k plus 6. And it's each of those outcomes with probability 1/6. And if you have 6 consecutive integers, exactly one of them is divisible by 6, right? I think we agree to that. Okay, and so therefore, this outcome is, the conditional probability of b is 1/6, no matter what happens with the first 100 dice. So we can finish by using this law of total probability. We say the probability of b divisible by 6 is probability of a100 times the conditional probability plus ... And the beauty of this trick is that we don't actually care what, let's say, the probability of a100 is. Okay, probability of a100 is not too hard to figure out, right? There's only one way to get 100. It's 1/6 the 100. But figuring out what's the probability of 303 is like impossible. But the beauty of this trick is we know all of these conditional probabilities are 1/6. So we get the sum over all probability of AKs times 1/6. So we can factor out the 1/6. We get the sum of all the probabilities. And these have to add up to 1 because exactly one of these outcomes between 100 and 600 occurs. So that's the end of the proof. Any question about that? Did it make sense? All right. We did it slightly elaborately, but okay, good. Now, this problem has a trick. That's why I only like it medium amount. It was good for illustrating this law of total probability. But here's a trickier problem. Let's say I roll 101 regular dice. What is the probability that their sum is divisible by 5? Can somebody tell me? No? Okay, that's good, because it's not that easy. You see, it looks similar, but just the trick does not work here, because if you roll the first 100 dice, you're on some number k. You're either going to get k plus 1 up to k plus 6, And it could be that one of those is divisible by 5, or two of them are divisible by 5. So basically, the trick doesn't work, and you're kind of screwed. Actually, this is the answer. Can somebody guess what this is approximately equal to? I mean, if I didn't even tell you the answer, what is your intuition? Yes, your intuition is, some people are saying 1/5. That's a good intuition. I mean, kind of seems like, I don't know, it's not obvious that it should, any number mod 5 should be different than any other number mod 5, so maybe around 1/5. Now, if I change this to 2 instead of 101, you could draw a little table and you would see it's not exactly 1/5, but you might feel that once you roll enough dice, it should sort of become like 1/5. And that's correct. I guess this is very close to 1/5. I don't know if you can read this, but let's 0.2 and then a lot of zeros and then 1. Yeah. So how did I get this number? Because it's a very hard thing to get. We can see later. In our lecture on linear algebra, we'll see why this is the answer. OK. Great. How are we doing on time? All right, let's talk about another important concept, which is independence. Now, you might have also seen independence before, but I have also a different perspective on it than most people, so let me tell you about that. This is, if you crack a textbook, this is the definition you will see. You just open it up, they'll be like, here's the definition. A and B are independent if probability of A and B equals probability of A times probability of B. OK, you probably saw that previously in your life. So now, that definition, they phrase it like that because they're trying to be very smart about not mentioning an extra case. It would be better if they described it in this more friendly way like this. We say A and B are independent if the probability of A conditioned on B equals the probability of A, or vice versa. Okay, and that's the same thing if you just, this line is the same as this line if you just divide by probability of A. Okay, except you can't divide by probability of A if it has probability 0, but that's a very stupid case that nobody cares about anyway. So this is basically the definition, and this is the one that has some intuitive meaning, right? Like, you would think to yourself, oh, probability of A and B are independent if, whether or not the probability of A occurring sort of is the same whether or not you condition on B. That has an intuitive meaning. Okay, so now in a common probability textbook, they'll just tell you that definition, and then they'll always ask you this question for some reason. So they say, if I flip 2 coins and let A be the event that the first flip is heads, and let B be the event that there's an even number of heads, and they'll say, are these events independent? So what do you think, yes or no? Who would say they are independent? Like 2 people. Who would say they're not independent? 0 people. What about the rest of you? What about you? I don't know who I'm pointing at. No? Should we try again? Who thinks they are independent? More people. Not independent? OK, well, I guess you've seen it before. Well, it doesn't look like they're independent, right? I mean, at an intuitive level, because you're like, well, I mean, A sort of depends on what happens with the first flip. B depends on what happens with both flips. So it doesn't look like they're independent. So that would be the answer. Oh, sorry, that would be a reasoning. But actually, the answer is they are independent. And here would be the proof. Well, just compute. The probability of A is 1/2, clearly. The probability of B that you get an even number of heads, it's 2 out of 4 cases. It's also 1/2. And probability that you get both, the only possible outcome is heads, heads. That's 1/4. And 1/2 times 1/2 is 1/4. So yes, they're independent. That is answer number 1. To me, answer number 2 is this is the dumbest question ever. And it's very pointless. Because it doesn't make sense to care about this. OK, in this problem, we can compute all 3 probabilities. So who cares if when you multiply 2 of these numbers together, you get the third number? It's not telling you any interesting information. And in fact, somehow this view of independence is never used in real life. Because there's a secret principle of independence that nobody ever tells you, but I will now tell it to you. That's how independence really gets used in life. And here it is. suppose you have a block of randomized code and you split it into two parts, like these lines and these lines. And suppose A is an event that only depends on the first part. Okay, like whether or not A occurs, you can tell just by seeing the trace of these lines. And similarly, B is an event that only depends on these lines. Okay, and suppose you prove using regular mathematical logic and reasoning, like we're all used to, that these two parts of code cannot affect each other. Okay, that's something you could prove using like logic and deduction. For example, you might show that like you could run them in either order, it doesn't matter. Then you can deduce that A and B are independent events. And therefore, you can deduce that probability of A conditioned on B equals probability of A. Now, this is the way that independence always gets used in real life. You like have some problem, you like have some events A and B, you sort of argue about why they're independent using this principle, and then you say, aha, therefore we can do a computation using this fact. Now, if you think about it, if you go back to these slides, like that does not make any sense because like formally our definition is like they're independent if and only if this holds. So like you can't tell that they're independent unless you already know this equality, right? But in real life, you figure out that they're independent and then deduce that. Okay, and this is basically a theorem that you could make formal that like if A and B have this property, then this holds. But once you know this theorem or this principle, this is how you actually use independence to compute things. Okay. Okay, so that's all about independence of two events. There's also a notion of independence of multiple events. And I'll give you the definition, I guess, when there's 5 events. So if you have 5 events, A1 to A3 up to A5, they're independent if, this is the definition, well, this is the natural generalization you would think. If the probability of the AND of all the events is the product of the probabilities. That's what you would think the definition might be. But it's not. You also need that the probability of the first 4 is the product of the probabilities of the first 4. And that the probability of like A1 and A3 and A5 is the product of the probabilities A1, A3, A5. And like for all the subsets, you need that this to hold. Okay, so there's actually like basically 2 to the 5 conditions here. In other words, A1 through A5 are independent if for every collection of them indexed by set S, which is a subset of 1 through 5, the probability of the AND of the events in that collection is the product of the probabilities. Okay, so you see when 5 is replaced by 2, it's basically the same thing because, well, the case when S is either everything or nothing is kind of trivial. Okay, but just as with 2 events, like you never use independence this way. Like you never sit around and like compute like all these probabilities and be like, aha, they're all equal. So great, I proved they're independent. Because you already did all the hard work, and now you're just making a random statement. Instead, use like a principle of independence that sort of holds for like 5 blocks of code. If you have A1 through A5, they all depend on like 5 different blocks of code, and you can prove using logic that they don't interact with each other. Then you can deduce that the events are independent and that you have these formulas. And it's not obvious, but it takes a little work, which I won't do, to see that if you know that A1 through A5 are independent, then it's not just like these formulas hold. All the facts that you would imagine are true based on the name independence are indeed true. Like this fact says that if A1 through A5 are independent, then conditioned on both either A2 or A3 holding and either A4 not holding or A5 holding, that doesn't change the probability of A1. So any event that like involves A2 through A5, conditioning on it does not change the probability of A1. That's like something that you can deduce if they're all independent. Does that make sense? Any question about that? All right. Oh, okay. This is the last thing that, see, this is so terrible that I'm doing this today because normally when I give this lecture, I have like cupcakes for the people whose birthday it is. That's a shame. Well, you guys really lost out this time. Anyway, the birthday problem. You've possibly seen this before. Maybe all of you have seen this before. Have you seen this before? Okay, nevertheless, there's going to be some aspects to it that you haven't seen before, so hang in there. Okay, so this is a well-known, super familiar probability chestnut that you've seen before. Let's look at it. There are m students in a room. What's the probability that they all have different birthdays? So now there are some issues here, which we were going to model. First of all, we're going to ignore like February 29th. And then we're going to also assume that every day is equally likely to be born on, which I guess is not true. And we'll assume there's like no twins. Actually, how much time do I have? 10 minutes. There's an anecdote I always tell here, which I cannot rob you of, so I'll tell you it. Maybe like Sang has heard it before. So I used to teach this other class here, probability and computing. And I talked about the birthday problem there. And I was like, oh, we're going to ignore like February 29th. And then just for fun, I was like, is anybody here actually born on February 29th? And like one kid like put up his hand and he was like, yeah, I was born on the 29th. And it like made sense. Like if I imagined what his age would be, it was like divisible by 4 in the appropriate way. And I was like, oh, cool. Like, let me see your driver's license. And so he like started to take it out. And I was like, no, I was just kidding. I don't want to see your driver's license. I believe you. But then the TA who was sitting in the class was like, I want to see your driver's license. And she was kind of a weird person, if I may say so. And so the kid was like a very friendly guy. He was like, okay, here, he took it out and he gave it to her. She was like, thanks. And so then I was like, whatever. And I started turning around to like write on the board and go on. And then like the whole class like erupted into laughter. And I'm like, uh-oh, what happened? Did like my pants fall down or something? And so I turned back and the TA is like taking a photo of the guy's driver's license with her camera. And I'm like, that's really weird. And so, I didn't know what to do, so I just like started lecturing it again. And like again, like laughter, I turn around, and the TA is like leaving the room with the guy's driver's license. And I'm like, well, I don't know what's going on. So like, she left all her stuff too. So I like took her like cell phone, and I like gave it to the kid, and I was like, make sure you get your driver's license back. And so then the class just went on as normal, and she came back, and she gave him his driver's license back. So then I asked later, like, why were you like, what happened there? And she's like, oh, I was really like intrigued and excited that his birthday was February 29th. And I was like, why did you leave the room? And she's like, the lighting was bad for like the photo I was trying to take. So that was my February 29th story. Is anybody here born February 29th? Okay, good. Sang might take your picture. Okay, so by this modeling assumption, this is what I mean. So this is how we model it. We've gone from all this ambiguous English to this. For I equals 1 to 5, m, student i's birthday is a random integer between 1 and 365. Yes? No. Well, I mean, it's kind of trivial if m is more than 365 by the pigeonhole principle, but we'll come to that. Okay, analysis. So apparently you've seen this before, so I'll go a bit briefly. Let AI be the event that the student's i's birthday is different from all the previous birthdays. So in this code, you're like assigning the birthdays one by one. And when you're doing the ith one, let's consider the event that that ith one is different from all the previous ones. Okay. And this is the event that we really care about, d, the probability that all the birthdays are different. And d is, I claim, the intersection of all these events, the and of all these events. So why is that the case? Can somebody say? You. Yeah. Yeah, I mean, the way that everybody's birthday is different is if, okay, the first person's different from nobody, and the second person's different from the first, and the third is different from the first and the second, and all the way up to the last person is different from all the previous ones. Okay, so we can try to compute probability of d by using the chain rule. First, we need to compute probability of a1 times probability of a2 given a1, a3 given a1 and a2, and so forth. Okay, so there's a lot of terms in here where like a term in the middle is like this. Probability of ai given a1 up to ai minus 1. Okay, so in English, what does this mean? What it means is we're conditioning on this event. So we're like assuming that the first I minus 1 birthdays are all different. And now we're asking what's the probability that the ith one is also different from those. Okay, that's what I just said. So it's sort of like after the I-1 birthdays have been chosen, we're assuming they're all different. So sort of like 365 slots for birthdays are there, and I-1 of them are occupied. And now the next person comes along, their birthday is chosen. Something awesome is happening up there. And it can go into any one of the 365 slots. And so the probability that's different from all of those is this. It's 365 minus I-1. These are the number of unoccupied slots over 365, which is this, 1 minus I-1 over 365. OK, now your objection becomes relevant. So this formula is actually not quite right if I is bigger than 365, because it's not like at that point they're like negative slots free. So we're going to assume, I guess, that yes, at this point, there's at most 365 students in the class. OK, so this is the probability. So we can plug that in and deduce that the probability of all event birthdays being different is 1 times this times up to 1 minus m-1 over 365. OK, and that's it. That's the final answer. We are done. That doesn't look too pleasant, so I'll say a few more words in a second. By the way, oh yeah, so as I said, like normally when I do this, I do the actual experiment to see if all of your birthdays are distinct. Now, in this case, with so many students, it's going to be almost surely. It's going to be like, the probability is almost certainly going to be 1. So the normal way you do this experiment is you go through all the students and like you count, they have them all say their birthdays, and if somebody hears their birthday, then they say, yeah, it's the same as mine, and you detect that 2 people have the same birthday. There's so many people in the class that it's actually quite likely that as soon as the first person says their birthday, somebody else already has that birthday. So we could test that. But then you can also say to yourself, well, there's no point in asking the first person for their birthday, because it's just like some random number between 1 and 365. You may as well use some other random number between 1 and 365, like today. So is it anybody's birthday today? No? There's about a 50% chance, I think, based on this number of students. Was anybody's birthday yesterday? Somebody's pointing. Really? Awesome. And he's the first person in the class. That's amazing. Wow. That's super awesome. Wow. And it was like the test. I'm sorry. I ruined your birthday. Well, anyway, if I'd planned this better, or I would have a cupcake for you, but I'll bring it to you next time. Awesome. Wait, can I see your driver's license? That's OK. I'm just joking. OK, so this was the final answer. You can plot this as a function of m. You see that like as m increases, or wait, what's happening here? As m increases, the probability of, I think this is the probability of, them having all distinct birthdays goes to 0. You can't see this, but this is logarithmic. This is like 10 to the minus 20 up here. This is like 10 to the minus 100. So with like 150 people, like the probability is truly negligible. So if you do a little approximation, it's actually, this is the probability of having 2 people with the same birthday. And you see it goes above 50% once there's like 23 people, which if you've never seen this problem before, may sound counterintuitive, but perhaps you're all used to it now. Let's see. OK. If there are n possible birthdays, right now we consider if there's like 365 different birthdays. If there are n birthdays, then the probability that you have m students to share a birthday is this. It's n instead of 365. And you might ask, for what value of m is this around a half? OK, so imagine there are n birthdays. What's the 50-50 point for when like 2 people are likely to have the same birthday? And you can solve this within calculus. It's not a calculus class, so I'll just tell you. It's basically root n. OK, so if you have n different birthdays, and everybody picks a random birthday, once there are about root n people, there's a 50-50 chance that 2 people will have picked the same birthday. There's a story here about cryptographic hash functions, but we only have 1 minute left. Well, I'll start and then stop in 1 minute. Actually, maybe that's a bad idea. Let's see. The point of this anecdote, which I don't have time for, is that this sounds just like joking around, but this birthday problem in real computer science is sometimes called the birthday attack, because it's intimately related with the security of cryptographic hash functions. So I mean, cryptographic hash functions, well, you kind of know what a hash function is, and attacks on them are based on this birthday paradox, that if you're trying to like find two quantities that hash to the same number, if the output range of the hash function is capital N, then you would only have to try about root n hashes before you get a collision, which seems a lot less than the n that you might expect. And so this is a way that people try to break these hash functions like SHA-1 and MD5 and stuff. And yeah, I don't have time for this. So yeah, basically, this person cracked SHA-1 based on this observation. And so the government was like, oops, let's now invent SHA-2. Maybe there's SHA-3 now even. I'm not sure. So there is a real application of this birthday stuff to computer science, but the class is over. So we'll see you next time.